So, in lecture number 5, we are going to discuss the working function of boost converter in details. So, we have seen that this is the circuit diagram for boost converter. We have earlier discussed this circuit diagram in details, and the difference with buck converter is that here the inductor is in input side, whereas in case of buck converter it was in output side. And similar to buck converter, the boost converter or step up converter also has two modes of operation. In mode 1, that is when the BJT is on, and mode 2 is when the BJT is off, right? Now from these two circuit diagram, now we will try to draw the critical waveform of boost converter. Now so these are the critical waveform similar to buck converter, from where we will decides the ratings and all the details of the components used in boost converter, that is the BJT, the diode, the inductor, the capacitor, right? Now this is, as we have mentioned, in case of buck converter, this is the gate pulse, which is also known as base drive pulse. And we know when this base drive pulse is high, that is in DTS period, the BJT is on, that is short circuited. And when this base drive pulse is low, that is 1 minus D into TS time period, that is the T off period, the BJT is off. So this is the gate drive pulse or base drive pulse, which control the switch on and off operation of the switch, that is in case of here is the power BJT. Now when we have discussed the buck converter, we have mentioned that basically this is here, this is the point P, which is BP, voltage here is BP, which is the pole voltage, and IL is the current through the inductor, ID is the current through the diode, VI is the input voltage, IS or IN is the source voltage, IC is the capacitor current, and I0 is the load current. Now in this point P, the voltage is Vp, which is the pole voltage, and this current IL, these two parameters, that is the Vp and IL, helps us to decide the rating of the components. Now if we see here that when the BJT is on, that means it is short circuited, so the voltage Vp here is, in this particular point, is 0. Now Vg is low means BJT is off. BJT is off means in mode 2 diode is forward biased, that means diode in conduction mode. So the charge, what has happened in inductor in this mode 1, now that will start discharging through the output. Okay, now this output is connected to the pole. So if here the voltage is V0, here also V0, and this voltage will appear here also. So now the voltage Vp equals to V naught, right? So if we see the waveform, so this is the waveform of pole voltage Vp, and this value is V naught. So when BJT is on, that is short circuit, the voltage is 0, and when BJT is off, the diode start conducting and that output voltage appear across the pole, and that time Vp equals to V naught, right? Now a little more discussion. Now during on time the BJT is short, right? So here the voltage is 0, here the voltage is V naught. Now in this condition, that is in mode 1, diode is reverse biased. So what is the peak inverse voltage that has to withstand by this diode? Is this V naught value. Similarly, when the BJT is off, that means the switch is off, that is in 1 minus dTs period, the voltage here is, the voltage V0 will appear here, V0 will appear here, this voltage V0 will appear here, and the BJT has to withstand a voltage of V0 in off condition, right? So basically this voltage Vp, the voltage, pole voltage here, this voltage at this point P is deciding factor for the voltage rating of BJT and diode, right? Now we have mentioned that IL is the current through the inductor. So what should be the nature of this current? This is similar to the nature of that triangular ripple kind of thing which we have seen in case of buck converter, right? So if you see the waveform, it will be just similar to what we have seen in case of buck converter. So IL will be in triangular ripple kind of waveform as buck converter. You can see this is a triangular in nature, right? But the value and significance will be the different than that of the buck converter. Now when BJT is on, means VG is high, pole voltage is 0, so it is in a rising slope. Why? If you see here, so this is V in, this is 0, so V in minus 0 divided by L is the current IL, and V in minus 0 by L is positive, so it is rising in nature. Now when BJT is off, this is V in, this is V naught, this is L, so the slope is V in minus V naught divided by L. Now if we think sincerely, then we know for this boost converter this V naught is higher than this V in. So if this V naught is higher than this V in, so V in minus V naught will be negative. That's why during the off period it is following the negative slope. So this is basically the slope of this portion is V in minus 0 by L, that is V in by L, and the slope of this falling portion is negative, that is V in minus V naught by L, and here V naught is higher, so the difference between V in and V naught is negative, so that's why it is falling in nature, and this was repeated. Now in case of buck converter, we have seen the average value of this inductor current was I naught, because in case of buck converter this inductor was connected in the output side. So I naught was the average current. But in case of boost converter, it is connected in input side. So in this case, the source voltage or the input voltage, that is Is or In, is the average current, right? So this red line, mentioned red line, is basically, I have forgot to mention it, this is In or Is. This is the input current or source current, is the average value of this inductor current. Okay. Now this inductor current in total time period, this period is T on, this period is T off. So T on plus T off is the total switching period T. So this inductor current in this total time period is consist of two parts. One part is starting from 0, rising, and then rising slope, and then it will become 0. And another part is, it's again from this part rising to Imax, then 0 and down. So basically this inductor current has two component, right? What is the two component? In mode 1 inductor charging, BJT is short circuited and the slope is rising slope. So the BJT, so the current which is flowing through this BJT, that is IQ, will follow the nature of the inductor current. So if we see the waveform, IQ has follows the nature of the inductor current. Now when IQ is off, when IQ is switch off, means it is open circuited, then the current is 0. So in this period the current is 0. Again it is follow the inductor current 0, follow the inductor current 0, and so on. So this is the nature of off current of the switch or BJT. Now another part of this inductor current is the diode current. So when it is gate signal is high, BJT is on, that is mode 1, that is diode is not conducting, diode is reverse bias, so the current is 0. So if we see here, the diode current is 0, and when it is in mode 2, that is BJT is off, that means gate signal is low, that means diode is forward biased, so it will follow the nature of the inductor current. So this is the nature and it will get repeated, right? Now in case of inductor current, we have mentioned the average was source current or input current, but in case of diode current, it is the I0, I0 is the average current, because if we see the circuit diagram, in this condition this current is the average current, because it is get divided into, this IT current is divided into two parts. One is flowing through this capacitor, which is IC, and another is flowing through this output R0, that is I0. And this I0 is the DC component, or average component, and the current which is flowing through this capacitor, its average value is 0, because in total period is charging discharging, so average value is 0. So that's why in case of inductor the average current was the source current, whereas in case in mode 2 in the diode, the average current is I0. And so that's why we have mentioned in waveform that average current is I0. Again I have mentioned that diode current is combination of this two current, right? The diode current is combination of this two current. One is the DC current which is flowing through the resistor, one is capacitor current. So if we think minutely, so this ID is basically combination of I naught and IC. So what is my IC? IC is ID minus of I naught. So this value is I naught. From 0 to this portion here it is I naught. And for capacitor current it is ID minus of I0. So we have to subtract I naught from ID. So if we do that, the waveform will become in this fashion, and here this is the I naught. So we have subtracted. So now this line is the zero line. Are you getting my point? Because ID equals to I naught plus IC, and this is my I naught. So what is my IC? IC is ID minus I naught. So I have subtracted. So now this line is the zero line, T axis, and this is the nature of the capacitor current. Same as the diode current, only thing is that it is subtracted from the diode current by I naught. So here the minus I naught. So this is plus I naught, and this is minus I naught. So this is the nature of the capacitor current. And we know in this time capacitor discharging, charging, discharging. So this is the nature of capacitor voltage. So these are the all critical voltage waveform of boost converters. Now we have discussed earlier that in case of boost converter, this voltage here in this point P, that is VP, pole voltage is responsible for voltage rating. Now what should be in case of current rating? What should be in case of current rating, right? Now we have mentioned earlier that for inductor current the average is I in, and for diode current the average is I naught, and this hatched portion is basically the diode current. So diode current average is I naught, and this hatched portion in red line is the diode current. We have seen in our critical voltage waveform just few minutes back. Now now for BJT, what is my average current? Is I in or IS. Now we know from here it is, I have forgot to mention it. So if we apply here ampere second balance, means ampere into time. So I in is operating for duty cycle D. So I naught equals to I in by D, or sorry, I naught equals to I in into D. So I in equals to I naught by D. Again same thing we can get from this because in case of any converter, output power equals to input power in ideal condition, because the no losses are taking place in all components like switch, inductor, capacitor, all are non-dissipating in nature. So V0 I0 equals to V in I in. So here we will put the value of V naught here, and if we simplify we will get I in equals to I naught by D. So this I in equals to I naught by D we will get both from this equation, output power equals to input power, or we will get from ampere second balance equation. Now if we see the waveform of inductor current or the BJT current, so this is my Imax. So this is my diode. In case of diode also it is Imax. This point is Imax and this point is Imin. So and this is my delta IL. So what is my Imax? My Imax is the average. My Imax is the average, that is I in, plus this part, and this total part is del IL, and this part is del IL by 2. So what is my peak current? what is my peak current which is flowing across this? So what is my peak current? Imax. So what is my peak current? Imax. In case of BJT and diode, it is I in plus this is delta IL by 2, because this whole is delta IL. So this will decide the current rating for both the BJT and the diode. Right. Now if we see in this waveform of this diode, now if we see here, we have mentioned that diode current is combination. We've seen that IC plus I naught diode, and we know IC equals to ID by I naught. We have mentioned when we have described the waveform of capacitor. So we have mentioned although that for that capacitor I naught is the zero line, and we know del Q equals to I0 into DTS, that is CV. Okay, because we know Q equals to C dV by dt. So you can write del Q equals to I0 DTS equals to C into del V. So from here we can simplify. We will get C0 equals to I0 into D by del V into Fs, because Ts equals to 1 by Fs. So all these values are given, so you can easily calculate this value of capacitor. Now my intention is to determine, just like as buck converter, the value of Lmax or Lmin, and what we have mentioned earlier, that when we will get the value of Lmax, the duty cycle will be minimum, that is Lmax for Dmin value and Lmin for Dmax value. So again we know V in by L equals to, because we know V equals to L di dt, so we know this del IL by del T from mathematics. So del T equals to DTS, because we have taken here the rising slope, and we have mentioned rising slope is V in by L. We can here also take the falling slope. In that case del T will become 1 minus D into TS. So here we have taken the positive slope, so we get the value L equals to Vn into D del IL by Fs, because TS equals to 1 by Fs. D is the duty cycle, and all these value are, if we know, which is given in our converter design aspects, so we can easily calculate the L. Now we have mentioned that Dmax and Dmin will determine the value of Lmax or Lmin. So when we will get the value of Dmin, because when the value of this numerator is higher, Vin is maximum. For same V naught, it will be D minimum, and for D V in minimum we will get the value of D max. And this maximum value of input voltage and maximum value of input voltage, minimum value of input voltage will be specified in our data sheet, so we can easily get the D max and D min value, and accordingly we can get the value of L max and L min. So this is overall the mathematical deduction of a boost converter. Later on we will see some other aspects to solving the problem, a different form of this CL and all these things, a different calculation methodologies. Basically these all are same in different format. So this is all about today. In next lecture we will discuss the mathematical aspects or the critical waveform of buck boost converter. Thank you very much.